Hello friends, last class I told about the organic light emitting diode, how it is working, and what are the main materials and the layers are required to design the organic light emitting diode. So now I am to discuss about the working principle of the organic light emitting diode and how it will work for different structures. Okay, so that I will discuss now. Organic light emitting diode. So first materials, 2-3 materials or layers are required, right? So one is the anode material, cathode material, and in between anode and cathode you can insert multiple organic semiconductor layers. Depending on the application, depending on the performance, we can add different multiple layers, right? So normally here I am just drawing normal okay, so this is a this is whole transport layer, electron transport layer, emission layer. This is the anode and this is cathode. Okay. So organic light emitting that is driven by the electroluminescence effect. Okay, so we have to apply the positive forward bias. Okay, so for that cathode should be more positive as compared to the anode. Okay, you have to apply more positive voltage at the cathode side as compared to the anode side as compared to the cathode side, right? So suppose 5 volt, if you apply the 3 volt here, 2 volt here, so net voltage you will get 1 volt. Okay, so now suppose I am applying here, it is positive, I can define as a positive terminal, this is anode, this is a cathode negative terminal. So the positive voltage I am applying here at the anode side, and negative voltage I am applying at the cathode side. Now last class again one thing I told that the work function, suppose this is the vacuum level. Okay, the work function of the anode should be as high as possible. Okay, like 5 electron volt. For case of the cathode, it is as low as possible, 4 or 3.9 electron volt. Okay, so this anode, the HOMO level, this is HOMO level and this is the also HOMO level. These levels are called LUMO level. The anode, the work function of the anode, that should be matched with the HOMO level of the p-type semiconductor or whole transport layer, and work function of the cathode should be matched with the LUMO level of the n-type semiconductor or electron transport layer to get the efficient injection of the electron and holes inside the device. Okay, so when we apply the positive bias, right, positive voltage at the anode side, the hole will be repelled from the anode, right? Hole will be repelled from the anode and it will transport into the whole transport layer, right? And here in this case the electron will repel from the cathode and it will transport into the electron transport layer. The whole transport layer, that so now the hole will transport through the whole transport layer by hopping mechanism. Okay, so by hopping mechanism, and it will inject it at the emission layer. Okay, here I will get the hole, right, and electron that will transport through the electron transport layer and it will be injected by the emission layer. Okay, here I will get electron. Why this thing is happening? Due to the forward bias. Okay, suppose this layer, the entire layer, the multiple layers are there, right? So suppose 3 layers. So the thickness of the 3 layers is very thin. Okay, suppose if we apply 5 volt, we will get a 10 to the power 4 to 10 to the power 5 electric field. Okay, volt per centimeter electric field. This much electric field we will get. So normally we will 0 to 10 volt power supply is required to inject electron and hole inside the device. Okay, so if we make thin layer, so less voltage is required for getting the high electric field. Due to the high electric field, the hole will be accelerated towards the electron, and electron will be accelerated towards the hole due to the, because the energy barriers are there, but due to the high electric field both will be accelerated into each other, right? So hole will be accumulated inside the emission layer, electron will be accumulated inside the electron emission layer again. So through the HOMO level and through the LOMO level. After that, what will happen? Due to the electrostatic force, this hole will be fall down to the HOMO level, from LOMO level to HOMO level inside the emission layer. When it will fall down from LOMO level to HOMO level, at that moment it will recombine with the hole. Okay, at that moment it will recombine with the hole and produce a light or energy, optical energy. Okay, due to the electrostatic force, the electron will be fall down to the HOMO level of the emission layer and recombine with the hole, and produce a light energy. This process is called the recombination process. Recombination process, and this zone where the electron hole recombine, at this place is called the recombination region. Okay, recombination region. This region is called the recombination region. Right. So the process is again defined as a radiative recombination process, because due to the recombination we are getting the radiation or light. Alright. So there is a non-radiative recombination. For case of the non-radiative recombination, we will not get any light. We will get the heat energy. Okay. So that is not suitable, applicable for the organic light emitting diode or light emitting diode. Right. Now, okay, now, so here I told that once the electron is recombined with the hole, we will get the light energy. Then the wavelength of this light, okay, or energy, that is equivalent to the visible wavelength of the visible light. Okay, that is equivalent to the wavelength of any visible light we will get. Depends on the material, we can get different kind of the wavelength. Right. So this the wavelength lambda, right, that is depending on the HOMO-LOMO difference between the HOMO-LOMO level of the emission layer, because at the emission layer I am getting a photon, right? So the lambda that is related with the difference between LOMO and the HOMO level of the emission layer. And types of the semiconductor. What kind of the semiconductor you are using in case of the emission layer? If you at the emission layer, if you use 2-3 multiple layers for different semiconductor, for different kind of the band gap, okay, you will get the different kind of the light from a same device, right? And then if you mix multiple semiconductors, we can mix multiple semiconductors for getting the different kind of the light. We can tune the organic light emitting diode, okay, from 400 nanometer to 700 nanometer by employing co-mixing of the different semiconductors, right? We will get the light from the same device, 400 to 700 nanometer wavelength of light by co-mixing of the multiple materials or molecules. Right? So this is about the working principle of the organic light emitting diode. Now I will discuss about the types of the different kind of the heterostructure. Heterostructure means what? So if it is a homostructure, so in this homostructure, suppose this is p-type and n-type semiconductor, both semiconductors are connected, but in this case the level, LOMO level for p-type and n-type semiconductor is equal, okay, and for HOMO level this is equal, okay. This is the homostructure. There is no energetic gap, right? But for case of the heterostructure, I have to apply different different kind of the HOMO label and the LUMO label. So this is LUMO 1, LUMO 2, HOMO 1 and HOMO 2. So there is an energetic gap at the interface of p-type and the n-type semiconductor. So this is known as hetero structure. Okay, so we can use the different kind of the hetero structure for getting higher performance or for getting long lifetime and the high brightness of the LED. Okay. The junction is called the hetero junction. The junction between the p-type and n-type semiconductor, this is called the hetero junction. Okay. First, I will tell about the single heterostructure. For case of the single heterostructure, only one junction is there. Okay, only one junction is there between two materials, right? So suppose this is the whole transport layer and this is the emission layer. Okay, this is the single heterostructure. Okay, the junction is called the and the structure is called the single heterostructure. The junction is the single heterojunction. Okay, so this is the p-type. You have to use the p-type material for whole transport layer. And for emission material, you can use the n-type. Okay, and therefore emission layer. In this case, what the recombination will take place, right? So normally, what will happen? The hole that will transport into the whole transport layer, the electron that will injected by the cathode and this is injected by the anode. Okay, that will also transport. That will be remain. The electron will be remain inside the emission layer. Okay, then but hole will be transport into the emission layer. Okay, it will be the whole transport layer helps the hole to transport into the emission layer. Okay, so the emission layer, this layer is the recombination zone. The interface. Okay, because due to the energetic gap, so electron, all the holes will not be collected into the emission layer. So hole will be accumulated. Hole will be accumulated at the interface of the hole HTL and the EL. And again electron will be accumulated at the interface of the HTL and hole, because due to the energetic it will not easily transfer into the whole transport layer. Same case in this also. So the boundary, this boundary of the whole transport layer and emission layer is called the recombination zone. But there is a one drawback. We will get poor performance. We will get poor performance and less lifetime in this case. So for getting high performance, instead of a single heterojunction, we have to use the double heterojunction or multi-layer heterojunction. Okay, what are these things? Single and the multi-layer, double and the multi-layer. First is the double. So by name, the double means two heterojunctions are there in this structure. Two heterojunctions are there. So I have drawn one structure. Okay, beginning of the lecture. So this structure is the double heterojunction. Again, I am drawing whole transport layer, the emission layer. So multiple, you can use the multiple semiconductor in this emission layer, depending on the color of the OLED. Okay, and here it is electron transport layer. I have already explained this thing. Okay, again I am explaining. So this is the anode and hole will be transport. So the electron transport layer, this energetic gap, this is less as compared to this energetic gap. Okay, if we apply the positive bias, due to the electric field, this hole will be collected inside the emission layer. Okay, but the hole will not be collected at the electron transport layer. Okay, this thing is not possible due to the large energetic barrier. Due to the large energetic barrier, this transport is not possible, right? Again, for case of the electron, okay, electron will transport through this way, uh, due to the this energetic gap, electron will not transport, okay, this transport and this transport will not possible. So what will happen? So more number of holes are accumulated, okay, inside the emission layer. In same way, more numbers of electron are accumulated inside the emission layer. Okay, in single layer, what will be some amount of the hole will be transport into the electron transport layer, emission layer. It will be collected by the cathode, and again the electron will be transported into the hole transport layer, and it will be collected by the anode. Okay, but in this case, whatever holes are collected by the hole transport layer, entire hole I am getting in the emission layer. Same way, so entire amount of electrons I am getting inside the emission layer. Whatever electron holes are injected into the device, so all numbers of electrons and hole will produce the light. Suppose 100 numbers of holes are there and 100 numbers of electrons are there. All the electrons and holes will give the light. But in case of the single heterojunction, so exact amount of light will not get. Okay, will get. So for that you will get the less efficiency. In this case, the entire electron and hole will recombine, and you will get the high efficiency and brightness. So you have to apply the low bias for getting brightness, high brightness. Okay, high. Low bias, but for the single heterojunction you have to apply the high bias for getting the high contrast or high brightness, right? So in this double heterojunction you have to apply the low bias. By applying the low bias you will get the high efficiency, long lifetime and the high brightness, because large amount of the electrons are hole are accumulated. These are not collected by the opposite electrodes, right? So this is about the double heterostructure. So two junctions are there, that is, it is a double heterojunction. Now multiple heterostructure. Heterostructure. So I am drawing the vertical structure here. Okay, so again, so in case of the multiple heterostructure, so you can get the multiple heterojunctions, more than double heterojunctions, right? So see, middle layer, that is the charge generation layer. A mixed number of the charge will be accumulated inside the charge generation layer. Now, so here I represent as OLED 2, OLED 1. So OLED 2 and OLED 1 both are also consist of multiple layers, 2 layers or 3 layers, right? So normally, so two different kind of the OLED structure are vertically placed, and these two structures are separated by the charge generation layer. One OLED is connected with the cathode and another OLED is connected with the anode. So here minimum 2 layers are there inside the OLED 2, and minimum 2 layers more are there inside the OLED 1. So here also you will get the electron transport layer and the hole transport layer in the same way. Okay, in same way we will get electron transport layer, hole transport layer. So the charge generation. So that means the electron and hole are accumulated inside the charge generation. Okay, accumulated inside the charge generation. From where we will get this electron and holes. Right, these will be electron will be normally collected by the cathode, and it will the OLED to transfer all the electrons inside the charge generation layer. Again, the hole will be collected from the anode, and the OLED 1 transport all the holes towards the charge generation layer. The band structure will be designed in such a way that the OLED will transport all the holes inside the charge generation layer, and OLED to transport all the electrons inside the charge generation layer after injection of the electron from the cathode. Okay, so it is like a similar like double heterojunction, but you have to, if you are getting more long lifetime, if you are getting long lifetime light, so normally here also from OLED 2 and from OLED 1 they will also produce the light, but few amount of light you will get from OLED 2 and OLED 1. So maximum number of the light or photons you will get from the charge generation layer. Okay, so so this structure is mainly used for multiple, for higher efficiency, with some applications if we require more brightness and long lifetime. So normally, so overall if you want to choose better performance OLED, okay, this technology you have to choose. Okay, so these are about the types of the heterojunctions, right? So normally this is suitable. This is suitable if you want to use the organic light medium for optical communication. You need the high data rate, right? You need high data rate. So for this case also more amount of the data is required from the OLED, right? So for this case we mainly require the multiple hetero structure is required. And double heterojunction, you can use double heterojunction for display and lighting application. So next class I will discuss about the more types of the organic lighting media for which are used in the different marketing and commercialized purpose, and what are the materials are used in for designing the organic lighting. There are many more materials, so I will discuss about the some properties of the different organic semiconductors. How can you choose the different kind of the organic semiconductor, which semiconductors are suitable for the OLED. So this thing we'll discuss on the next class. Thank you.